going to go ahead and get started. So if you haven't had a chance to take a seat, please do. Super excited to see everyone here for our second session of the day in this room. So for those of y'all that don't know, this is sort of a faculty-led initiative, but then it's been taken on by students, by staff, by community members, and it's been just a great chance to reconnect with folks. I'd ask y'all to silence your cell phones if you haven't already to minimize disturbance to the presenters. And there's going to be a 15-minute question and answer session towards the end, so you can save your questions till then. I'd like to introduce our organizer for this session, Dr. Caitlin Crossett. Dr. Crossett is assistant professor in the Department of Atmospheric Sciences. She joined the department in 2023, and she teaches courses across many different topics, including climatology, weather forecasting, oceanography, programming and software tools, as well as scientific writing. She's most interested in not only understanding each weather event individually, but also the interaction between people and weather events and how that interacts with forecasting and application of weather models. So thanks, Dr. Crossett, for organizing this, and you can introduce our panelists.
Good morning, everyone. Thank you for being here. So our first talk will be by Dr. Doug Miller, and he's going to talk to us about the unfolding of Helene as witnessed by two gauge networks in western North Carolina.
Thank you. So since I'm the first speaker, I'm just going to say the three of the presentations are partly the result of funding that we got from the NC system known as the Collaboratory. And so we're going to be summarizing and hopefully finishing, at least at the end of this year, what we've been doing. And so some of what we're presenting today are the results of that study. So my focus is going to be following this outline. And it's hard to understand that actually the chain of events that you and I remember from September 27th actually got started 10 days before September 27th. So this is the drought monitor output from September 24th. And if you look in eastern Tennessee, they are under pretty extreme drought. And just across the border, the drought is not quite as extreme. And so as we're going through this talk, just think about the soil kind of as like a sponge. So it's got a lot of air pockets in it. And so it can hold a fair amount of water. And once you start filling up that sponge, its ability to hold the water becomes compromised. At this time, September 24th, the soil in western North Carolina is already holding some water because of this event. 10 days before, September 17th, we had a low pressure system and a front that were both kind of stalled out right over western North Carolina. So for over a 24-hour period, there's almost a steady amount of rain. You and I have long since forgotten, since what happened, on the 27th is kind of stuck in our memory. But the Asheville airport reported 2 inches of accumulation on this day. So if it was falling that heavily over the airport, it was falling pretty much all over western North Carolina. And so that's why we did not have an extreme drought on September 24th. But now let's get into talking about the days leading up. And everyone who was here probably has some memories of those days. So we'll start first on the 25th. These 2 days, the 25th and the 26th, leading up to Helene, were part of what is known in our field as a predecessor rain event. You've probably heard about that if you've ever been looking through the media and kind of summaries of what happened that day. So on the 25th, what you see, this is a surface pressure map, so we can see that the frontal system and the low pressure systems at the surface were just not moving. They were stuck in place. And the air mass immediately east of the fronts is bringing humid air from the Gulf of Mexico up into the mountains. And anytime you move humid air up against the mountains, that's going to force rising motion that results in clouds and precipitation. So everything really started on the 25th, immediately after what happened on the 17th. If we look at a satellite image, you can kind of see the main problem is this low that's just spinning. It's a cutoff low in the mid-atmospheric levels. And when that gets cut off, it does not go anywhere. And that then allows this really humid plume of air to move northward from the Gulf of Mexico. That cutoff low that we see in this imagery did not move for a couple days and really didn't even move until it started interacting with Helene. So if we look at a map of moisture plume, the gray zone here is showing us that moisture that's immediately moving in from the Gulf of Mexico. And so, of course, anytime you move humid air up against the mountains, this is what you get. So this is Wednesday night before. This is looking at an animation of radar snapshots. And of course, the oranger or redder the color, that means heavier precipitation is falling in that area. I don't know if you all remember that Wednesday before, I took the bus from here to go back to my hometown in South Asheville, and Hendersonville Road, already at about 5 p.m., was starting to show signs of problems. And I knew when I saw that the Wednesday before, and then based on what we knew was going to be happening over the next couple days, that we were in for a long couple of days. So let's move into the next day, the 26th. So of course, all eyes want to look down in the Gulf of Mexico, but again, same thing, that front and low pressure system in the mid-latitudes just is not moving because that low we saw in the mid-atmosphere is just cut off and parked, literally parked. So all that humid air, again, is streaming up, but this time now, at the end of the 26th, now we're starting to see the beginning impacts of Helene. So if we look at a moisture map, again, that's showing us that connection to the Gulf of Mexico, there was a constant stream of humid air moving, starting in Asheville, all the way from Wednesday night into the time of Helene. Let's look at the radar on the 26th. And so again, look at that ribbon of cloud, heavy precipitation stretching all the way from western North Carolina down to the Gulf of Mexico. And then later on in this loop, you start to see what look like the rain bands of Helene starting to emerge. She crossed the coastline at about midnight between the 26th and the 27th. Notice the red polygon, that's the Storm Prediction Center saying, okay, these people in this area now need to not only be thinking about a hurricane, but also the chance of tornado. Red polygons means tornado. You start seeing small red polygons. Those are the Weather Service saying there is a tornado warning now in this area. You will also see occasionally yellow polygons. Those are severe thunderstorm warnings. And then you see green polygons a lot. That's flash flooding. So this is on the 26th. Before there, you can start to see Helene starting to emerge there in the panhandle area of Florida. All right, let's talk about Helene. So here we are. One thing I do want you to note, of course, it crossed the coastline of Florida at midnight and retains its identity as a hurricane until it gets into South Georgia. So if you see the shaded in symbol, that represents a hurricane strength storm. And then after that, as it's moving further north, it's not shaded in anymore, and that represents a tropical storm. So it's been knocked down in intensity a bit. But what I say happened here in western North Carolina, we were at a high-end tropical storm event. And so you probably saw some of the wind reports as it made its way into our area. Some of the higher elevations, we're still seeing gusts that qualified as hurricane force winds. So significant wind event. But notice its track, and that's going to be kind of important because of the disparity in what happens as Helene makes her way through western North Carolina. We'll just go with the moisture blob. You can see very clearly now how Helene is bringing very much humid, very tropical air into the area. And of course, that's the source for the incredible rain rates that we saw on the 27th. So let's now go to the radar. You can see still tornado watch area. There's tornado warnings that come out on occasion. But what I really want you to look at is kind of the orange area associated with the basically dying out eye wall. Everything that is located underneath that dying eye wall is going to experience extreme rain and extremely high wind gusts. And that eye wall kind of splits its way between us and maybe Haywood County a little bit to the west, and then goes straight north. So if you go to a little bit further west of Haywood County, People are saying, the 26th, that was terrible, but Helene, not so bad. But for us, because we were located underneath that dying eye wall, we had a much different experience. And then look at this, at the end of the loop, there are flash flooding polygons everywhere in western North Carolina. So what we're going to do now is we're going to compare rainfall observations from two locations, two networks. One of the networks I'm responsible for, located in Haywood County. We'll see a map on that here pretty soon. And then the other has been in place for many, many decades down at the Coweta Hydrologic Laboratory. If you're familiar with that, that's down in Macon, Georgia. So we'll take a look at a map here to show you kind of where these different locations are. So again, my gauge network is in Haywood County. The Coweta place is located down here in Macon. And I'm just showing you kind of the river basins that they're located in. The one in Haywood County is in the Pigeon River Basin. The other is located more in the upper Little Tennessee River Basin, and it's really kind of a small sub-basin. So here's the network down there in Macon, 9 rain gauges. You can see the elevations top out at about maybe 3,500 feet, so 3,500 feet and below. Some are in the ridge line, some are in lower valley locations. And so here's that rain gauge network and the observations of hourly rainfall going all the way from the 25th into Helene. Now, we're scientists, so we have to use the metric system, right? So you're saying millimeters, what good is that? Well, right around just above 25 millimeters corresponds to about 1 inch. So you can see that for the most part, most of the 9 rain gauges were reporting well below 1 inch an hour, which an inch an hour is actually pretty impressive. But the thing to take note, if you block things off into 24-hour periods, that in the Macon County Coweta Hydrologic Rain Gauge Network, they actually had more rainfall on the 26th than they had happen on the 27th. And again, that's because they were just a little bit further west where that remnant eye wall was not making its way into their area. So these are the total amount observed, all 3 days thrown together. The highest amount was 13.6 inches. And that happened mostly on the 26th, so not even associated directly with Helene. Let's do a comparison now to Haywood County. So these are the locations of the 32 rain gauges. They're entirely at high elevation, so our lowest rain gauge is at about 3,500 feet. We've got our highest one is out in Mount Guillot at about 6,500 feet. And I'm going to focus in just on 3 rain gauges and what they observed over the 3-day period. These 3 rain gauges had a very good direct link to what was observed at the Newport USGS River Gauge during the Helene event. So the big winner in terms of this particular rain gauge network in the Pigeon River Basin is down there, not far from Camp Daniel Boone, with a 3-day total of just about almost 16 inches of rain. That's rain gauge 11. And of course, if you look right next to it, higher elevation observes only a total rainfall amount of 8.5 inches. That seems counterintuitive, and it should seem. Generally, higher elevations get a higher amount of precipitation. So I'm scratching my head looking at this saying, is this real or is this some sort of problem with instrumentation? So as I'm driving to that rain gauge 11, this is what I see. This is a debris flow in the East Fork that feeds right into the headwaters of the Pigeon River Basin. This is a debris flow that I have no idea where it starts up on the mountain because I wasn't about to try climbing up that, but it is a substantial amount of mud and debris that have come down the mountain. Just a little bit downstream of this, a typical story out there in rural western North Carolina. What used to be a peaceful little creek became a raging torrent on the 27th and was deep enough that it pulled the bridge apart, and 5 homes on the other side now are suddenly without any way to get out of their homes. So if we do the comparison, red is the Haywood County Pigeon River observations. Blue are from down in Macon County at Coweta. You can see that for 24-hour period, the Coweta gauges all experienced their heaviest rainfall on the 26th and uniformly have a drop-off when you look at the 24-hour period over the 27th. My part of the collaboratory study is partnering with the NCDOT organization. And so let's take a look at some pictures of what they actually filmed the day of Helene's passage. So you've probably seen some good videos and pictures of this, and probably have seen in the news that they are now estimating they won't be finished fixing this until the summer of 2028. This is a huge engineering feat. If you ever have a chance to drive through there, maybe you don't need to travel anywhere, just drive through there to see the whole production. It's unbelievable how much material they're having to bring in to fix this basically landslide. So let's look downstream at the Pigeon River in the Newport gauge. I'm just going to take a quick trip back to show you. I should have pointed this out. In the map up here, notice the red plus sign. That's Newport, Tennessee. We're going to be looking at a USGS gauge from that. So that's located on the Pigeon River. Everything that happened in the western North Carolina part of the river basin is going to be felt and observed at that river gauge. So here is the report from basically a week centered on Helene. The National Weather Service goes to all the USGS locations, and they decide what qualifies as a minor, what qualifies as a moderate, or a major flood. And so at this particular gauge, 12 feet is what qualifies as a major flood. Look at the peak from Helene. 29 feet was what was reported, so more than double what the Weather Service considers a major flood. If you look at the rate of the flow of the river past the gauge, this is what you see. They didn't even calibrate to be able to adjust for what the actual flow rate was. So it's literally off the charts. And so based on some preliminary work, those three rain gauges that I pointed out early on have the greatest correlation to what is seen when we lag between the rainfall and what was observed at the river gauge. And so there seem to be two epicenters, probably where the very inner edge of that remnant eye wall traveled over. So everything that I've highlighted in the thick red represent that area that correlates very well to the USGS river gauge at Newport. And in the far northwestern upper left corner, those are all green. That's the national park gauges. Anything that happened in the national park has a very low correlation with what was observed at the USGS river gauge. So what that implies then is, again, the eye wall most likely made its way over in the middle and southeastern part of Haywood County, Pigeon River Basin, and the far northwestern part was spared the destruction. So let's go look at some hypotheses. There's two things that could really have explained what we observed, at least in our rain gauge network. One is that the winds coming from the southeast were in the perfect direction to take that humid air and get the maximum benefit of lift from the mountains. And so that's probably why there was just widespread issues on the 25th, 26th, and 27th. That explains a lot of the overall average rainfall. But there are things, because of the eye wall moving over the area, that there are small convective elements, and you've probably even seen this. The wind damage is very spotty. You can drive along the Blue Ridge Parkway and see no trees in one area, and then just go half a mile away, and it looks like nothing happened. And so there's something else going on that's beyond just linked to the mountains. And so the hypothesis is that as this eye wall made its way over the mountains, that the eye wall was reducing the strength of the mountains were reducing the strength of the updrafts needed to keep that eye wall going. And so that the eye wall elements were possibly collapsing and creating mini microbursts. This is a hypothesis. I have no way of proving that absolutely right now, but we, of course, have a lot of hypotheses that we're going to be testing, hopefully, in a follow-on study to what we're doing now. And this was what I personally experienced on that morning. So it has, of course, some personal investment on my behalf as well. I do want to thank some students who ventured. I mean, it was an adventure trying to get out to these rain gauges last fall. So Bryce and Zachary, my wife was dragged along a couple times. Ranger Paul Super helped out tremendously, and then a couple other students, Piper and Andrew, and then my colleague and friend at the Waynesville Watershed, Don, helped navigate in February to go try to recover the rain gauge data on the Waynesville watershed. So that concludes my talk. I know we'll have questions at the end, so make a note if you're like me and I will forget my question in 1 minute. So thank you.
Thank you, Doug. I am up next, so I'm going to get my PowerPoint up here. Great. Well, again, thank you for coming, or those of you that came in a little later past our initial welcome. I am Caitlin Crossett, an assistant professor here at UNCA in the Atmospheric Sciences Department. So as Dr. Miller was mentioning, this study is really a big collaboration amongst us in the Atmospheric Sciences Department, some of our students, and then I specifically worked with weather forecasters at the Greenville-Spartanburg National Weather Service office. So if you don't know and you live in Asheville, that is your local weather service office. So look at their website for any kind of inclement weather information. And then also Carl Schreck at the North Carolina Institute for Climate Studies was also a collaborator on this study. And I'd like to also mention that Bryce, who helped Dr. Miller go to some of his rain gauges, was one of my student assistants on this project. So as a nice follow-on from what Doug was talking about, I'm going to go over this high-resolution wind analysis of Tropical Cyclone Helene. So as a quick background, right, we all know if we were in Asheville, or we learned from Doug's presentation, that Tropical Cyclone Helene produced at least tropical storm force gusts across most of western North Carolina and upstate South Carolina. This map here behind me, it was created by the National Weather Service in Greenville-Spartanburg, and you can see, I've kind of pulled the legend out so you can actually read it, that there were these larger pockets, right, of 70 to 80 to 90 mile per hour winds, so up in that hurricane force gusts, in a very small area. Let's see if I can find the laser. This pink right here, kind of northeast of Asheville, where we saw some frequent 80 to 90 mile per hour wind gusts with pockets of 100 miles per hour. Of course, we know, right, there were widespread power outages across Buncombe County and western North Carolina. And if you were here for Greg's talk, he mentioned just the absolute devastation of forests around western North Carolina, with 822,000 estimated acres that were lost, right, or damaged. And this accounts to a $214 million amount of money that was damaged. And this was from the North Carolina Forest Service report in October of 2024. So here is just a plot of these winds. So this is from the North Carolina EcoNet. So just a network of observational weather stations that are kind of dotted across North Carolina. So if you've never gone to the North Carolina Climate Office's website, they have amazing graphics and you can get local information. And so they put this graphic together, and we see that the highest gust, you see this little flag, 106, not surprisingly was on the top of Mount Mitchell. And it's estimated that these gusts are actually lower than what we experienced, given that we lost power, right? We lost internet connectivity, and so we lost some data as a result of that as well. But you can just see that the widespread tropical storm force gusts across western North Carolina. So it's really no wonder that we had a ton of forest damage. And as Dr. Miller showed us, right, we had a ton of precipitation. So you're on these very steep slopes, super saturated soils. A wind gust will very easily knock over a tree. So this is also from the North Carolina Forest Damage Appraisal, so their report. This is publicly available. And what's plotted here in the blue is light forest damage, up to the yellow there is severe forest damage. So the highest amount of damage is here in McDowell County. But what we see, right, is if I kind of go back, that black star on our wind map is about the same county there. Our highest wind gusts right? We're not located in that same region. So when I was talking with the folks at the National Weather Service and Carl at NCICS, we see, right, this mismatch, or what we see as from our initial observations and our forest damage, between the strongest observed gusts and, right, where the most significant damage was. So this presents some forecasting challenges for National Weather Service forecasters, right? So how do we message these risks if the fastest wind speeds aren't actually in the locations where you see the highest amount of forest damage? So what we have done is completed this high resolution wind analysis. So we used this weather forecasting model called the High Resolution Rapid Refresh, or the HRR, as we like to call it, or the HRRR, depending on your preference. We used this to characterize surface wind gusts, right? I mentioned that these observational stations are just dotted across the landscape at uneven intervals. We also lost power, right? So we're not seeing the entire picture. So what we wanted to use was use this model, right, to get a more smooth representation of what occurred over the event and to kind of understand if this wind damage was actually a mismatch between these strongest observed gusts and the forest damage. So this GIF here, created in GIS, so if you were also at Greg's talk, right, is gusts greater than 45 miles per hour. I did have this in meters per second, and I decided to put it in miles per hour. So yes, we are scientists, but just for understanding for all of us in the room, right? And you can see, right, as Tropical Cyclone Helene makes its way, right, through Western North Carolina, we start even before Tropical Cyclone Helene, its center moves into Western North Carolina. You'll see that there are some pretty strong wind gusts happening mostly right in the high terrain here, where we saw a lot of the tree damage and some of those fastest wind gusts. So the threat for wind, right, is not only due to this decaying eye wall, as Dr. Miller was saying, but it's these outer rain bands and the large system itself that causes some of this damage. I don't have it in this presentation, but we looked at some of the time that these regions were exposed to these high winds, and for some locations it was 12 hours was the maximum that some of these high-end locations were experiencing these high wind warning level gusts, or within a tropical cyclone or tropical storm force gusts. So then what we did was we just pulled the maximum 10-meter gust, right, so 10 meter off the surface from this HRR model, and I looked over 18 hours of the 27th, right, that's when we were experiencing most of the gusts from Tropical Cyclone Helene. And I say tropical cyclone, right, to encompass both that hurricane, the sustained winds that were hurricane force and tropical storm force. And you can see, right, in miles per hour, there are regions here that have greater than 94 miles per hour gusts, right? In that same region that the Weather Service pinpointed that kind of elevation dependence there. But across most of Western North Carolina, again, we experienced these tropical storm force gusts. So no wonder, right, we had all of this tree damage. So what I did, again, if you were at Greg's talk, so it was a great transition into this, is I used the high-form data set that NEMAC helped develop with the USDA and the National Forest Service. And so they classified these 4 different types of tree damage based on the extremity and the size in acres of tree damage. The one that I'm going to focus on most is outlined here in red. So this type 1 damage, I don't know if you can read that, but it's extreme. NDVI is the normalized difference vegetation index. So the NDVI is basically the change, right, from when we have healthy vegetation to, in this case, when all of our trees are damaged or unhealthy. So it's this metric that allows us to see not only vegetation health, but in this case, right, where we have a ton of trees that have been damaged. So these extreme damage polygons in kind of GIS language or regions were anything that was greater than 1 hectare. And right, there are these massive blowdowns that you can see here along the Blue Ridge Parkway compared to these other 3 damage types, right, where we have heterogeneous impacts or just a few isolated blowdowns, or right, maybe the top of the tree just fell off and maybe that tree was just a little unhealthy, right? And so we're only focusing on these type 1 extreme events. So what this looks like from satellite, this is along Elk Mountain Road, kind of east of Asheville. You can see, right, just the extreme amount of trees that are down. and you can see all of these tree trunks, right, are lying in the same direction. So this allows meteorologists to know that this is straight-line wind damage versus something like a tornado, which we'd see trees being thrown in kind of like a circular pattern. And so just massive amounts of tree damage there. And then here's a field perspective of that from the same location, right? So standing on that road, looking out, right? Maybe some of you live in this area or you've been there, right? And so just absolutely, completely blown down damage. So what we wanted to do was compare these maximum wind gusts with this extreme damage to see if there was any correlation or if there was kind of a match with these highest wind gusts and this damage. So on this plot, right, this is the same plot as the maximum 10-meter wind gusts from that HRRR model, but now you'll see the orange-ish little polygons there, and that's from that high form data set where we see the type 1 or the extreme high severity forest damage. So I'm just gonna zoom in to, this doesn't work, to Mitchell and Yancey County, right? Greg also mentioned that, I think he said in Mitchell County 50% or that it's estimated that 50% of their forests were completely, blown down. So while we see there is, right, some match, right, and here near Burnsville or north of Burnsville, some of those higher gusts are representative of where we have some of that really high severity wind damage. There are places, as Dr. Miller mentioned in his talk, right, here in McDowell County where we only have 58, I say only, right, 58 to 62 mile per hour wind gusts, and we have significant, right, tree damage there within that region. So there is more to the story, right, than we can just say, yes, these higher wind gusts are correlated with more tree damage, and that we hope to altogether, right, kind of figure this out moving forward. So to put numbers to this, right, because I think seeing it on a map is one thing, but actually quantifying it is something different. What we did was in GIS, you can overlay, right, the area that had these different wind gusts. I will mention, I do have meters per second here now, so sorry for the confusion, but if you just multiply it by 2.5-ish, you'll get to miles per hour. And so we calculated how much of that actual high severity damage area was located in each one of these thresholds. And this 26 meters per second gust threshold here is what the Weather Service uses as their kind of bottom thresholds, for lack of a better word, for when they will produce a high wind warning. So a high wind warning will go out and it will have some sort of impacts associated with it so that you know, right, if you're in an area with a ton of trees, you should, be mindful of not being there, right? So this is why we chose that 26 meters per second threshold. And you'll see, right, that if we just look at each of those individually, we kind of see this ramp up around 31 meters per second, and then that flattens out. So within this region, right, we get 11 to 12% of that high severity damage area happening at each one of those gust thresholds. But if you just look at the cumulative percentage, so I'm just adding all of these up together, right, to fit this nice curve, 98% of that high severity damage fell within that high wind warning threshold, right? So this means, one, that these National Weather Service thresholds are valid, right? And two, that the wind had some impact on where we saw most of this high severity damage. But maybe you're thinking, okay, well, 98%, that's not 100, right? So the remaining 2% of this damage occurred outside of this threshold. And so as Dr. Miller was mentioning, we're thinking this may have been due to these really small storm scale or convective processes like microbursts or these things called tornadic scale vortices. So they're not tornadoes, but they're more circulations that are on a very small storm scale that could have produced these intense gusts that we just can't see using, radar or any of our observations. And so for future work, we're gonna compare all of the 4 types of the damage. I only compared the one, right, the highest severity, with our surface gusts to see if we can tease any more of these relationships out. Again, as Dr. Miller mentioned, we're gonna look at this elevation dependence. A lot of these really large areas of a high severity wind damage happened at higher elevations. So can we correlate or figure out if the acreage or the size of this high severity had some dependence on elevation, or, right, if we're at lower elevations, there was actually smaller damage, and it may be related to more of these storm scale processes. And the last thing, which will be the most time-intensive thing for us, right, is doing these high-resolution simulations of Tropical Cyclone Helene. So the HER data that we used is only 1 hour. It's resolution, so we only get output every 1 hour. And we can't really see any storm scale features just on a 1 hourly temporal resolution. So really dialing that down to sub-hourly resolution and also making the spatial scale of those grid points smaller as well, so we can see these really isolated storm scale features. And so that is all I have. So thank you. And next up, we have Dr. Elaine Godfrey, who is a adjunct professor in the Atmospheric Sciences Department here at UNCA, and she will be talking to you all about how well did numerical forecasts predict the record-breaking flooding from Helene and its predecessor rain event. Great.
All right, thank you so much, Caitlin. It's interesting to be here talking about this about almost 1 year ago is when we were seeing Helene coming to this area. And what an event that was. And it's hard to believe it's been a year. What a year. So Dr. Miller and Dr. Cross's presentations lead in really well, looking at how well the river models forecast this event. So I'm a numerical modeler. I did numerical modeling work once upon a time with weather models, and I was curious about how well the river forecast models did, so I decided to look at the forecast models to retrospectively compare those to our observations. So this is a picture from our street that we took when the power was out and the cell phones were out, and we needed to get motorists who was stranded, who tried to drive through high water, out and on the morning of the 27th. All right, great. So the numerical, the National Water Model uses a WRF hydro model. It takes input for lots of observation types. It takes the soil moisture into its computations, and it takes the weather forecast, the forecast amount of rain, and it runs different numerical models and simulates how the water that falls is going to interact with the soil. And it simulates the land surface processes, and it uses water routing models and things to try to forecast how well how high the rivers are going to get. So there are medium and long range forecasts. They're put out for a few days in advance. There's 4 times a day, it does a 3-hour look back. So it's incorporating data from the last 3 hours. And those do pretty well, and they're updated more quickly every 6 hours. And once a day, it does a 28-hour look back. And when it incorporates that data from the past 28 hours, it actually does a pretty good forecast. So if you're curious about the National Water Model, you can go on to this website, thewater.noaa.gov/map at any point in time. And these are all the different stream locations it does forecasts for. So the Lower Mississippi River Forecast Center on the afternoon of the 25th issued this display cautioning that there are going to be some major flooding events. And they actually mentioned, the Southern Appalachians and the French Broad River Valley, the Pigeon River, Tuckasegee, Swannanoa, and so forth. So 2 days out, we're looking at this. They're looking at the forecast rainfall, which, mouse doesn't show up. We're expecting a lot of rainfall here. So this was shared Wednesday afternoon, about 1:21 Central Time, so 2:20 in the afternoon. It got 5 likes and 4 shares on Facebook, 486 views, 1 repost on the site formerly known as Twitter. And so it didn't really get the reach that you would really expect, because how many millions of people live in this region? All right, so the next day, on Thursday, NOAA issued a really rare operational weather event news release saying they're going to expect widespread outages. This is going to be a really big event. And they even used this wording: it would inundate communities in its path with flash floods, landslides, and cause extensive river and stream flooding. And gusty winds combined with saturated ground will also raise the risk of falling trees that can cause loss of life, property damage, block roads, and lead to power outages. The only thing they missed were the communications outages and the water service outages. We're missing those. But they otherwise did a really good forecast here. And then the Weather Service on Thursday afternoon issued a really strong statement of catastrophic flooding and landslides. It could be one of the most significant weather events to happen in the western portions of this area in the modern era. We plead with everyone that you take every single weather warning very seriously. You can't get stronger wording than what the Weather Service issued the day before. Landslides, including fast-moving debris flow consisting of water, mud, falling rocks, trees, and other large debris, are most likely to fall within small valleys that drain steep slope. Most of us have never witnessed a landslide, right? And even before Helene, I mean, we knew they could happen. We kind of figured they might happen in big mountains. No, they can happen here. All right. Then the Lower Mississippi River Forecast Center issued this really incredible forecast. This is issued Thursday afternoon. And, all right, they're forecasting actual record-breaking river crests for the French Broad and the Shenandoah River, which, if you understand how models work, they work on past data and past observations. So in the past, we've seen with these conditions, this kind of thing happens. The models were actually forecasting it to break all the records of the past, which is really incredible and a success story. This was issued Thursday afternoon. It got 4 likes, 0 shares on Facebook, and 367 views on Twitter. This should have been everywhere. Every person should have seen this. And a lot of emergency management did a great job getting the word out, but somehow we have this lack of communication between the experts and the people who are looking at this stuff and the everyday people. You know, I teach high school math, and I told my students, you know, go fill up your tanks with gas on Wednesday afternoon. But otherwise, they had no idea anything was coming. All right, let's talk about some observations. So this is the other Dr. Godfrey and our youngest daughter observing the French Broad River near my folks' house in Fletcher. Normally the channel of the river is right here. It's very shallow and smooth and calm, and this is all a farmland, many acres that's all flooded out. All right, first let's talk about the Shenandoah River. That's the biggest one that hit this Asheville area. So it flows from east to west, draining through Asheville, and has a gauge here in Biltmore Village. It's a monitoring location. All right, so this is right, you know the fancy McDonald's that used to be downtown, or in Biltmore Village? Yeah, this is the parking lot, and McDonald's is over here. So typically, you know, the river's running about 2 feet, maybe 3 feet high. This is a action stage. Minor flooding is 10 feet, 15 feet. The road level is about 15.7 feet or so. So as of Wednesday morning, so Wednesday the 25th, we're going to look at our forecast river levels. So this is the forecast for the Shenandoah River that began at, okay. So I'm going to talk about everything in GMT time. Sometimes we call it Zulu time. So this is Greenwich Mean Time, which is 4 hours ahead of where we are in Eastern Daylight Time. So this is issued about 10:46 a.m. This forecast occurred. So it's showing the 26th, it's going to be minor, reaching up. Here's the minor flood stage, moderate, and then up to major flood stage, reaching 15.5 feet on the 27th. So as of Wednesday, they knew this was going to happen. They run some new model runs. This is late Wednesday night. Model was saying the same thing with Thursday morning. Then they did that 28-hour look back and got a new forecast, which was showing a forecast of over 20 feet. And the previous record for the Shenandoah River was not even 21 feet in 1916, so the really big flood that everybody talks about. So as of Thursday afternoon, they knew this was going to be as bad as the 1916 flood. And then Thursday evening, the models were saying the same thing. And then by Friday morning, we had even more data included, and they were showing it would be far above the record, so 27 feet. And that's where it actually crested, was at 27.33 feet. And for reference, the Water Service gives some, here's the level of the Moe's restaurant in Biltmore Village. The floor level is 18 feet, so 9 feet above that. So we have, here's an image by Mike Morrell. Here's the Moe's sign, if you can see that. And another view, there's Moe's again. So the Shenandoah River, usually very, very small, but the models did a really good job of forecasting that this was going to be an extreme event. All right, let's talk about the French Broad River, the big river in the area. So we're going to start about the upper French Broad River, which begins up here south of Brevard. Here's Hendersonville, and the Blantyre is the station where we'll look at measurements, where it typically floods the road. Again, you get heavy rain, they talk about flooding at Blantyre. that's pretty low and flat there. All right, so I'm doing the same thing, but I'm not going to step through every time frame. The initial forecast for Blantyre, we're also pulling it up above major flood stage as of Wednesday morning, a Wednesday morning forecast. But by Thursday afternoon, we knew it was going to be really high, way above major flood stage and way above the previous record of 27 feet, also from 1916. And the observation at Blantyre is 28.43 feet. The gauge was destroyed partially and damaged during the storm, but based on the high water marks, they were able to estimate the height was about 28.5 feet. So we move up a little bit, move down the river, which the French Broad River flows from south to north, near the airport along US 280 and Fletcher near the Ag Center. All right, very calm river, great for canoeing, just a peaceful place, lovely little park there. And as of Wednesday afternoon, they were forecasting major flood stage, well above the major flood stage record and the previous record, which was set in the big events of 2004. And it did indeed crest at 30 feet. So this is a huge difference. It crested over 10 feet above the previous record. All right, moving the French Broad River up to Asheville. So UNC is up here, just across the ways. The Asheville flood gauge here. Our forecast was showing, as of Wednesday, we knew it was going to be high. Thursday morning, by the Thursday afternoon run, we could tell we're going to be way above major flood stage. And the previous record of 23 feet from 1916 was indeed eclipsed to 24 feet. Moving further downstream to Madison County, the lovely, beautiful town of Marshall, as we all know, was hit pretty hard by the French Broad River, which is very wide and flat in this area. And as of Thursday morning, they still thought it was going to be almost major flood stage, not quite, but when that big look back happened, suddenly we had this huge jump. And so we knew almost 24 hours in advance that we were going to be reaching major, well beyond major flood stage and eclipsing the previous record from 1973 by, let's see, many feet. So we knew in advance, so people could get out. And it did indeed hit a record of 20.08 feet. And there's Marshall, which is slowly resuming. And if you get back up there, go to Zuma's. It's a great coffee shop, and they have great cookies. All right, lower French Broad River. Let's go to Madison County and the town of Hot Springs, which was affected by the French Broad and some other small creeks that came in the area. And you look at this river gauge, and you think, this is really tall. How could the water possibly get to be that high? And it was forecast to almost reach major flood stage with the models. We knew it was going to be bad. And it eclipsed even those, and it was over 22 feet. And lastly, we'll go to Newport, Tennessee, the same site that Dr. Miller was talking about, where both the French Broad and the Pigeon River come in. So the Pigeon River's here. We'll talk about that gauge in a few minutes. So this is the Newport, Tennessee French Broad gauge, which also was, as of Wednesday, was forecasting it was going to be a big flood. By Thursday afternoon, we knew it was going to be record-setting, or close to record-setting. That's the only one that actually didn't break the record and have a new record, and that's from March of 1867, right after the Civil War. All right, let's talk about the Pigeon River, which flows through the beautiful town of Canton, North Carolina, where Chris and I bought our first house. And Canton is no stranger to floods. They were flooded really badly with the double whammy tropical cyclones in 2004, and also again with Tropical Storm Fred in 2021. And the Pigeon River is this lovely little mountain stream. It's great for fishing. It's just beautiful, playing in the stream. And we could tell by Thursday afternoon it was going to be reaching major flood stage, or close to it. And I've got to give really big credit to the Canton Emergency Management. They learned a lot from Fred and their even other storms, and they went door to door with their fire department and knocked on doors. And as far as I know, I haven't been able to find any record of any deaths in Canton area. So they got everybody out. They knew there was going to be the damage, but they got the lives saved, which is really incredible. It's a great success story. So the previous record was from 2004, which is 22.8 feet, and the recent flood was only 19.6 feet, which only, it's horrible. I mean, this is almost 27 feet above the normal, 1 or 2 foot observation rate usually is. And so the entire town, downtown, a lot of it was flooded. So here's the normal riverbed But they're building back and building back stronger, and got the mill land sold, and hopefully everything's going to be redeveloped in a way that allows room for the river to expand as it needs to. And then Pigeon River flows down into Tennessee. Again, we'll look at the Newport gauge of the lower Pigeon River that Dr. Miller was talking about. And it reached its major flood stage and eclipsed that by a lot again. The previous record was 23 feet set in 1902, and it reached almost 30 feet, which is, for a river that's normally 2 feet deep, it's hard to imagine it can actually happen. But the models actually did a pretty good job of capturing that. All right, so the Nolichucky River, if anybody's driven up I-26 and to East Tennessee, you can see the damage to the Nolichucky, which is also this lovely little small mountain stream river, and it became a torrent unimaginable, and many lives were lost there. This is not as good of a success story for the water models as the other ones, probably because they had so much rain in the drainage basin. So Yancey County and Mitchell County are drained primarily by the Nolichucky River that flows into Unicoi County in East Tennessee. And they got a lot of rain. They got some of the highest rainfall totals. So Mount Mitchell, all of that area, it's draining this way. And the gauge is located in Embryville, Tennessee, so on the other side of I-26. So as of Wednesday afternoon, the forecast was for just barely above action stage, not even reaching minor flood stage. Thursday morning, they were thinking, well, not quite moderate. So, be on the lookout, be flash flood watch. But by Friday morning, we realized the model runs, they were running this model like right after each other, trying to get different results, you can tell. And they were not able to capture it at all. The highest, even as it was like occurring, is only 22 feet as captured by the model. But the river, the gauge was completely wiped out. It took several days to rebuild it. Data resumed, I think, October 3rd. The data they observed was 33.88 feet, and this had to be established from high water marks because the gauges weren't able to calculate and measure this. So I've got to say the water model didn't really do a good job of modeling how the Nolichucky was going to respond. I don't know how that's run, what kind of data they were incorporating, if they were able to get all the radar data. Of course, Dr. Godfrey is going to talk about some of the radar data holes in western North Carolina. Maybe that would help if we're able to get better radar data to go into the models. And we could have gotten those factories and the hospital evacuated and things, because the hospital was flooded there. Here's where the Nolichucky River crosses I-26 in East Tennessee, and which is all back open now, the 4 lanes. All right, to conclude, this is right outside. Lexi, thanks for this picture. Riverside Drive here, there's the chocolate place there. Okay, so the National Water Prediction Center Service did a great job with their forecasts. So their forecasts were issued 1 o'clock in the afternoon on Thursday afternoon. The only thing, I couldn't find any forecasts that they had issued directly for Nolichucky. So I put this in italics just based on the water model data I could find. But most of the forecasts that the Water Prediction Service did were really excellent. A little low, but you kind of expect that because we're record-setting events. They forecast record high levels for the French Broad at Blantyre and Fletcher and for the Pigeon River at Newport, which is amazing in itself. And we observed here, so the difference is less than a foot for the French Broad River. Up in Asheville, it was 3.5 feet off. The Pigeon River, they were about 8 feet below, and Newport, Tennessee, almost 12 feet off. So we still need some room for improvement. Swannanoa is about 6 feet below. And 6 feet makes a big difference. 6 feet vertically can be dozens of feet horizontally, depending on the slope. And the Nolichucky River was pretty badly off the model forecast from what was actually observed. And all of these, except for this one point at Newport, are all new records for the river heights. Okay, and I'm going to leave you with this quote. Nowhere in the United States, so far as known to the writer, are the streams subject to such frequent and marked changes in volume and to the degree to which they are loaded, as in those which have their source in the Southern Appalachians. This is a quote from Professor Alfred J. Henry from the National Water Bureau when he visited Asheville after the 1916 floods. And if you need to reach me, here's my email address. And thank you very much.
Thank you, Dr. Godfrey. And next, we'll have the other Dr. Godfrey, Dr. Chris Godfrey, who is professor and chair of the Atmospheric Sciences Department here at UNC Asheville. And he'll be talking to you all about potential radar coverage gaps in western North Carolina during Hurricane Helene and its predecessor rain event.
Thank you, Dr. Grosset. Let's get right in. Let's start with a radar tutorial, because not everyone in here is a meteorologist, although I know we do have some students. So with a radar, it sends out a beam of microwave radiation. This is the same stuff that cooks your Hot Pockets, more or less. And that energy bounces off of stuff in the atmosphere, and then we get some power back, and the quantity of power that we get is related to how much or how intense that precipitation is. So when we do this, we send it out in this little beam that goes out at a particular elevation angle, and the radar spins around. That would be tilt 1. And then we go up a little bit, a fraction of a degree, and then go around again. And then we go up and go around again. So in the end, we get multiple tilts, multiple slices through the atmosphere. Now, let's say we have something in the way, a mountain perhaps. Those lower tilts are going to hit the mountains, and we can't see beyond that. Or maybe some of those tilts will be partially obstructed by the mountains. So we get maybe a little bit of power back, but not a complete picture of what's out there as far as precipitation. So that brings us to this example. A lot of people have noticed for a very long time that we have a problem with beam blockage here in the mountains in western North Carolina. So here's a great example. This is not a tropical system. This is from a thunderstorm complex that moved through last year. And you've got the different tilts here. The low-level tilt is on the left, and then we go up into the atmosphere, tilt 2, 3, and 4. And you can imagine as we're going higher in the atmosphere, we're going to be able to see more of the storm because it's being blocked less by the mountains. But if you look over here, you see this sort of sector, and the radar location is right down here at the laser pointer. So you see this sector where, wow, there's not a whole lot of precipitation there. And again, that's because it's blocked. So there's a nice example of that. And we also have some folks at the Weather Service who recognize this issue as well. Now, there's a lot of tiny writing here. This was last year. This is from NWS Chat. This is a conversation that Weather Service forecasters will have with emergency managers and university partners and other folks in the community, media. And I want to highlight this little section here, and because that's really small and you can't read it, I'll make it bigger. And it says, "It's always tough to assess storm structure as activity moves through the mountains due to beam blockage." Now, this isn't really something that you're going to be able to get officially from the National Weather Service, but everyone knows it. So, yeah, there's a problem there. And we've actually tried to fix this a lot. There are several attempts to do this. Back in 2017, some of my colleagues and I at UNC Asheville and some other folks around the region put together a proposal to build a radar in Buncombe County that would cover western North Carolina. And that proposal was for $2.5 million. We sent that off to NSF. NSF said, wow, this is a really great idea, but we're not going to fund it because you don't really have the staffing to handle that at UNC Asheville. And well, yeah, they're kind of right. We all teach 4 classes at a time. We don't have time to be setting up radars and programs to manage that. So that same year, the administration, the presidential administration, told Congress to develop what ended up being the Weather Research and Forecasting Act of 2017. And the idea there was that they wanted the Weather Service to study gaps in NEXRAD radar coverage, and report that back to Congress. NEXRAD is the Next Generation Weather Surveillance Radar 1988 Doppler. That's the whole thing. NEXRAD WSR 88D is the radar. So they went ahead and did this report, and they said, you know what, there are no gaps in NEXRAD radar coverage across the entire country. Everything is fine. This network is great. Please look the other way. And at the end of that report, it says, but if you really want to fund something, we've got all these priorities that you can send money to for the National Weather Service. So you kind of see what they're doing there. They're saying, well, we don't really want to spend money on this thing that we kind of already have, and maybe there are some gaps, but we'd really like to fund our other priorities. Well, The Weather Service did end up lowering the standard low-level tilt by a little bit at 10 different sites and a few more later. And one of those was the Greenville-Spartanburg site, which covers western North Carolina. So we're just aiming it more into the mountains. Well, okay. So recognizing this problem and problems elsewhere in the state, there's a coalition of folks that call themselves the North Carolina Radar Project, and they are trying to get federal funding. And so these folks got together, and we had a meeting in Raleigh with the Director of Emergency Management for the state, and the NOAA Radar Operations Center sent a few folks from Norman, Oklahoma to talk with us. And we also met with Mike Clampett, a representative in the General Assembly here in North Carolina. And the general consensus was that, yes, we would like to seek funding to put some radars out here in North Carolina. Some folks said, well, we need one for the Charlotte area, because they're in a real hole. And then some folks said, well, we need a radar out in eastern North Carolina because there's beam blockage out there from trees on an adjacent property, and the owner won't cut them down. And I said, well, let's put one in western North Carolina and join the party, because we have beam blockage out here too. And so the result ended up being a House bill that went into the North Carolina General Assembly. And I'll highlight the fun parts here. It's for a radar that would be, well, it would be administered by UNC Asheville. So the funds would come to us. And all we're asking for is $17 million. Plus $250,000 a year to sort of run things, hire somebody to actually run the radar. Yeah. So unfortunately, in that session last year, the funding was limited to $2 million per request. So obviously, this didn't make it. So we tried again. And when we did that, all we're asking for is $18.6 million. Inflation is real, folks. So we're also trying to work with some federal partners to join and send us some money to put 3 radars here in North Carolina. And so one question we might ask is, how do we actually convince these people to fund a radar? And we've got to show, yes, we really do have a beam blockage problem. Well, wouldn't it be nice if we had some sort of a widespread rain event? And, well, we did. Okay, we had a storm. And so we can compare the actual observations from rain gauges to what the radar says is happening and see if we can find some beam blockage or evidence of beam blockage. So yeah, here's a set of pictures of my family in the top left here, minus a daughter. But this is a tree on our road. It's the same one that Dr. Godfrey showed a little while later. And in fact, underneath, this branch right here is this branch right here. So the water came up quite substantially. And so we sat on some trees and walked on some trees. And that's the river, by the way. This is in my yard. So, you know, we're kind of nervous about that river coming up. But anyway, we had a lot of rain. And hopefully this will work. There we go. What you're looking at on the left here is the lowest tilt from the Greenville-Spartanburg radar during the entire predecessor rain event, followed by Helene. On the right, you've got the composite reflectivity. Now, the composite reflectivity looks at the highest reflectivity in all of the available tilts from the radar. So it'll pick out the highest reflectivity in a column in the atmosphere. So that's a little bit closer in this area to what's actually ending up falling on us. And you can see some of these missing pieces here in western North Carolina. Let's watch that one more time because it's really fun. Here's the predecessor rain event, and it rains a lot. And eventually, here comes a tropical system, and there's Helene. And then it's a sunny day. All right, so let's get into the weeds a little bit here. And I've got some definitions for you. MRMS is the multi-radar, multi-sensor system. And QPE is quantitative precipitation estimation. So the idea here is that we are looking at a whole bunch of inputs radar, and generally with MRMS, it's also gauge observations and numerical models, kind of fill things in as well. In this particular case, we're not including rain gauges and we're not including numerical model adjustments, so it's just a radar estimate of precipitation totals from individual radars. And we've got 3 on this map. We've got the Morristown radar in Tennessee, that's right up here. And then we've got the Greenville-Spartanburg, GSP, right down here. And then we've got Columbia, South Carolina down here. And of course, we've got the escarpment with mountains here, and then we've got the mountains along the North Carolina-Tennessee border as well. And we can also point to this piece right here and see that there's this spike of precipitation that shows up. It's not real. It's the radar beam bouncing off the mountains and coming back. So it's not actually raining quite as much there. And you look at Buncombe and Madison counties here, and you see that, well, it didn't really rain much here. And of course, that's not true. And I'll tell you, there's my house, and there's some guy out in my yard measuring precipitation at 7:06 a.m. on September 27th. And I'll tell you, it rained a whole lot more than that 1/4 inch that's shown in the MRMS plot there. It was raining pretty hard. Well, MRMS also has a radar quality index, and this basically indicates the uncertainty that there is in the quantitative precipitation estimate. And that uncertainty will decrease, and this is a good thing, with, actually that's a bad thing, sorry. Uncertainty decreases with beam blockage, and that's something that's not going to change. We're not moving the mountains around, at least not today. And although Helene did a good job of moving the mountains a little bit. Anyway, so the beam height is also a function of the uncertainty, or vice versa. The uncertainty is a function of the beam height, and that's really a function of the freezing level, and that's corrected for by numerical models. And what you can see here is that, yeah, there's really bad coverage way out here. So poor Charlotte needs a radar. But we've also got some pretty low radar quality here in Buncombe County and in the Madison County, and then a little spike here along the eastern portion of Buncombe and Henderson counties as well. So let's take a look at the entire event, the quantitative precipitation estimation from just the radar for this entire event, a whole 72 hours. So we're going to start in the evening hours of Tuesday, the 24th, which in UTC time is midnight on the 25th. And we're going to go all the way through until it was sunny. And so this plot here shows you the total precipitation, again, from the radar, and you see this swath of heavier precipitation to our east, and then a lot of heavier precipitation down near the escarpment too. Some of that is not real because the radar beam is simply bouncing off of the mountains down there at the escarpment. So let's pick a few spots. My favorite site is the UNC Asheville weather station right here. We measured 11.43 inches with our tipping bucket rain gauge, and the radar estimated 9.09 inches. Well, that is a 20% error. Oops. Okay, the radar is underestimating the rain here at UNC Asheville. Well, all right, let's pick another spot. How about Mount Mitchell? They got a lot of rain. 24.45 inches was measured by the Econite site there near the summit. The radar says we got 18.72. That's a 23% error. Oops, we're underestimating again. How about one of Dr. Miller's gauges? This is number 107. This is just north of Clyde in Haywood County. 10.78 inches versus the radar's 7.69. Oops, 28.6% underestimation. Ouch. All right. How about Bear Wallow Mountain? 26.6 inches. That is a lot of rain, folks. And the radar only caught 17.7 in its estimate. 33.5% error. Ouch. Well, surely the radar just underestimates everything, right? Well, how about Anderson, South Carolina? The gauge measured 8.23. The radar got 10.86. That is an overestimation compared with the observations of 32%. Wow. All right, so let's look at some observations. Again, this is back at UNC Asheville, and this is a really complicated plot here. There are a lot of things going on, so let's take it in pieces. The x-axis here is time. Again, this is in UTC time, so subtract 4 hours if you want local time here in Asheville. And let's look on the left. So you've got the black lines and the red lines. The black lines are the rainfall rate in millimeters per hour given by our tipping bucket rain gauge. The red lines are the rainfall rate indicated by the radar. And so you see this, this spike right here. Let's actually zoom in a little bit, and we'll take the rest of the plot here. I'm going to zoom in on this part right here and kind of stretch it out for you so we can see what's going on. So again, the black and red lines, let's compare those. You're looking at nearly 125, 130 millimeters per hour. That is 5 inches of rain per hour. That's that rainfall rate, okay? 25.4 millimeters in an inch. So that's a lot of rain happening in this short time period. And in fact, that evening, one of our students, I think it was Andrew, Andrew's here, or he was, sent me a picture. Where did Andrew go? Anyway, Andrew sent me a picture from Robinson Hall of the first floor that was flooding. We got about 3.5 inches in an hour to an hour and a half. And so all that water was pouring in off the quad. So that's a lot of rain. And you see that the radar and the gauge are actually pretty similar. Now let's look on the right-hand side here. You've got the blue line and the green line. The blue line is the total accumulation from the rain gauge over this whole time period. And the green line is the total accumulation indicated by the radar. And so they actually do, or the radar actually does a pretty good job of matching the total accumulation, give or take, during this time period, especially in this really heavy precipitation. Now that's when we have some probably tall convective towers, and those higher scans are able to see the higher reflectivities way up there in the higher parts of the sky. Now in this area here, we've got lower rainfall rates, but far on the right over here, the gauge has a higher rainfall rate than the radar. So at that point, the gauge then outruns the total accumulation from the radar. Let's go back. Here's the whole timeline again, and let's focus on just the right side now. And again, we're going to zoom in and change the axis a little bit, so you're only going up to 40-some millimeters per hour here. And what really stands out to me here is that the rain gauge is seeing higher rainfall rates during this long or prolonged rainfall with fewer convective elements, more or less. And then the radar is seeing lesser rainfall rates. And then if you look at the green and blue lines, you'll see that they're diverging over time. And that means that the gauge is getting more and more and more precipitation compared with the radar. So there's an underestimation here, and this kind of feeds into the total underestimation that we saw at Asheville. All right, so is there a gap in WSR 88D radar coverage in western North Carolina? Well, let's say probably, yeah. And in fact, that probably might be a substantial underestimation due to beam blockage here in the mountains. Now, it's important to recognize that all rain gauges underestimate precipitation. That's just a part of measuring rain. Tipping bucket rain gauges are actually awful, especially in really intense rainfall. They miss a lot. So those gauge estimates that are way above the radar estimates are still missing a substantial portion of that rain, just because of the physics of how these things work. We also need to recognize that the gauge observations are something that forecasters are relying on in addition to radar, but then if we lose gauge observations, which has happened, let me tell you a story. When we had Helene and the power went out here at UNC Asheville, our rain gauge observations were not relayed anywhere. They didn't go anywhere because there was no way to get them out. And in fact, most of the North Carolina Econet sites and most of the automated sites, including the ASOS site at the Asheville airport, is gone. It's out. So the forecasters can't see that. They can't see what's happening in real time. All they have to rely on is the radar. And even back in when Tropical Storm Fred hit, and especially Haywood County and west, our weather station was down at that point. It was a it was a Wi-Fi antenna issue. And so we couldn't relay our information, and then they really missed the beginning of Fred's rain event because the radar is just not that great out here. All right, so there's certainly more work to do with this particular project. I want to do a whole bunch of site comparisons. We need to look at statistical significance of this underestimation, and then look at the azimuthal dependence of that underestimation. Clearly, it's maybe overestimating in South Carolina and underestimating in North Carolina. So we want to look at that. And also look at the beam height above ground level, because what we're looking at here is actually thousands of feet above Asheville. That's the lowest elevation that we can see. And the really interesting weather, the stuff we live in, is much closer to the ground. So things like rotation in severe thunderstorms that we might look at for tornadoes, we can't see that here. So, all right, that's where I'll leave you. And a public service announcement here. If you would like to contribute to rain gauge observations, then join COCORA's, the Community Collaborative Rain, Hail, and Snow Network. So you can stick a rain gauge in your backyard if you visit that website. All right, thank you all, and we'll bring it back to Dr. Crossett.
Okay, well, now is the time. We have, about half an hour for questions. The session's over at 11:45, so I'll open it up to questions. We have our mic runner here, so just raise your hand if you have a question. If not, I have a few prepared.
My question is for Chris Godfrey. If a radar site was established in Asheville, I know Asheville is kind of a bowl shape surrounded by mountains. Wouldn't we just have a similar problem with beam blockage in the surrounding counties if we did have a radar in Asheville?
It would be better than what we have now. And we're actually not putting it in Asheville. It would be on Bear Wallow Mountain. We've already spoken with the owner, and she and her kids are cool with the idea as long as we pay them a little bit for rent. So it would be up on Bear Wallow Mountain, so it would look over many of the lower peaks and hills around the area. So it would basically fill in what we're missing from the radars in Morristown and Greenville-Spartanburg.
Thanks. This is for Dr. Crossett. You mentioned that you were only looking at the type 1 tree damage. Is that because that's the type of tree damage that's most likely caused by wind? I would think about like landslides and other things that would damage trees, or like, the sediment being like really wet or things like that. Is that because that's more likely to be type 2, 3, 4 damage?
Yeah, so great question, thank you. That wasn't necessarily why we chose it. It was just kind of the first cut of what the tree damage that we saw across the landscape, how that was related to the wind speed. And so the future work portion of that is to look at the relationship between the type 2, 3, and 4 damage to see if there's the same dependence on the wind speed, or if there are other factors that are more explanatory, right? Like, the saturated soils and maybe lower wind speeds. We don't really have an extensive soil moisture network, right? It's really difficult to, number one, site a weather station, and to do that with soil moisture, it's a lot harder. So we can kind of get at that using precipitation estimations. But it was just kind of our first look at the tree damage versus the wind speed.
This question's for Dr. Elaine Godfrey. So the models you talked about and how they seem to have good agreement with some of the river heights, but not all of them. Mm-hmm. So these models, are these like general models, like internationally or nationally? Or are they specialized for Western North Carolina?
No, they're a national model. It's a national water model. And so they are incorporating data from weather models that are forecasting how much rain we're going to get, and they're also incorporating satellite data and groundwater levels and the current river status and stuff. Mm-hmm. But I think some of the failures, maybe especially with the Nolichucky, was the lack of radar coverage in Mitchell and Yancey counties. I think that probably played into how well it was able to incorporate the observed rain to figure out how high the water is going to get. And because it was missing a lot of that rain, it couldn't put that into the model to say we're going to have more water than we expect.
And then just as a follow-up question, do they parameterize the models for like the local geography, the local topography? Because the Nolichucky Valley is very curious topography.
Yeah, it's very steep. They do include the topography in there. Good questions. Thanks.
It's loud. Yeah, quick question. So seeing all the information about the high rainfall rates and, even with modeling, even if it underestimated the rainfall rates, how are your, I guess, you all, school, or any local meteorologists communicating this information with authorities or, people who have any charge over say-so, I guess, with weather warnings?
So, Adrian, you're asking, did we communicate what we saw as far as observations to other people who could disseminate that information?
Yeah, pretty much. Or beyond just y'all, kind of like, were y'all aware of just what efforts were on the way to kind of, just tell the general public of what was about to happen?
Yeah, so the data that we collect at our own weather station here go into the North Carolina EcoNet, and then the EcoNet disseminates that via their website, and then the National Weather Service knows where to look for that. They've got methods for ingesting the data. So in that way, the data were communicated, but we didn't call up anybody at the Weather Service or emergency management. Perhaps we should have. The Weather Service did a great job, but Jared wants to. Jared knows more than I do about that.
Yeah.
So I want to push on that a little bit, and I was thinking about this, and this is more of like a comment to not only the professors but to the students in the room. How do you communicate that 2 feet of water are going to fall? Right? Like, it's not, the Weather Service is down in Greer, right? They take the forecast and issue the stuff. But I think somebody asked in the previous session about, like, how do you get that information from the forecast to the person that take actionable information? And, like, how do you communicate that? And I think, like, the science is great. Your talks were amazing. But when you say that, when there's a flash flood emergency, when you say it could be a 1916 event, when you could say it's a 1 in 1,000 year flooding event or rainfall event, how do you convince that? How do you relay that information to the public so that you get that holy crap moment, I got to do something? And I know that's not a hard question, or that's not an easy question to answer, but it's like a philosophical thing I've been thinking about. And I just challenge that to anybody here to really just think hard about that, especially the students, because you're the ones that are going to be going out to the field down the road and dealing with this.
So I'll follow up. We had 3 weeks to the day ago, we had a landslide workshop here on campus. And a lot of what we learned in that session was that people really don't trust a source unless it's someone that they know giving them that information. So that's a huge challenge. The Weather Service, it doesn't matter how much money you invest in getting the word out. It looks like, in follow-up to what happened with Helene, that people only acted when someone in their family or their friend network said, this is going to be bad. So that is a huge challenge.
I want to make 2 points. One is that the Weather Service in Greenville-Spartanburg did an absolutely amazing job. That forecast was spot on. And they did say this will be catastrophic, this will be worse than the 1916 flood. They showed a picture of the 1916 flood and said worse than this. So it was a fantastic forecast that they made. So great job to them. The second thing is that we did actually reach out to, let's say, some people. I don't want to throw anybody under the bus, but we reached out to some folks and said, hey, we'd like to help you with messaging, and this is going to be really bad, so please, let's have a conversation about this. And they said, no, thanks, we got it, we're good, and then really dropped the ball. So that's unfortunate.
Well, I'm going to add in one more bit. I think it all falls to all of us. We need to stay aware, and we need to get the word out to as many people that we can. And I feel a little guilty for not posting all over every social media app I have, hey, watch out, this is bad, get ready, fill up your gas, get your water. And I see the forecast, but I think, really, is it going to be that bad? And it really was, because it's so beyond our realm of experience.
right? How do you visualize 28 feet of water in river arts, right? Like that is outside of any, I think, of our imagination until you drive down there and see where there's debris, right, up in the power poles, so, yeah.
So this is a follow-up question to messaging. I had just arrived from overseas. I was in Nashville, and what I noticed is that there seemed to have been mixed messages to different people. So I happened to be renting a basement apartment which flooded, and I had no idea. It wasn't even near a riverway. It was on the mountainside, and so I don't know where the water came from. But what I found out later is that a friend of mine in Weaverville, she was receiving text messages early in the morning of catastrophic and imminent flooding. Those are very strong words. I'm not a meteorologist, I'm a wildlife biologist, but those are very strong words to hear from a weather forecasting. I received no text messages. I was connected to a network. So some people were receiving stronger messages than others, and some of us no messages at all. So the people I talked to in Nashville, they keep saying, we weren't prepared. We didn't know what was going to happen. Do you have any, and I'm sorry I missed the first half an hour. If that was covered in the first 30 minutes, I'm sorry, but I'm just curious about that. Thank you.
Yeah, I don't know if any of us have an answer to why some people didn't get warnings, right, versus others. All that to say, right, we know that the Weather Service did a great job. Dr. Godfrey showed us the river forecasts were great. So I think it's also falls to, right, us educating the public where to get that information, right? Maybe it's from your local news or the radio, or you're just getting in a habit of checking the National Weather Service every day or something like that. But it's really difficult because, I don't know, half of the people that I know don't even check their weather app to know if it's gonna rain, right? And they get caught in a rainstorm that has been predicted for days, right? So that's not really an answer to your question, but since we are not, none of us are really social scientists, and we didn't have anything to do with any of them.
I will say, do sign up for the county warning alerts, because every county, like Buncombe County, has a warning system that you can sign up to receive messages on your phone. The Weather Service does have permission to the emergency flood, what is it? I forget the exact wording, but there are some like extreme emergencies where they can push through to all cell phones. Other than that, it's good to be on your county warning. I don't, do you get your county warnings for Buncombe?
I know about it now, so would you say that a year out, where it's better, that more people will know?
I hope so, but it's just kind of word of mouth, I suppose. There's no good, 30, 40 years ago, everybody got their same news from TV, radio, newspaper, and it's so spread out and diversified now. It's a mile wide and an inch thick. Everybody's just got to share as much as they can, I think.
And we lost power early in the morning.
That's
So
true.
so many people who should have gotten the message didn't get it because cell towers were out. That's a huge challenge. A lot of emergency managers in Western North Carolina are now starting to invest in very powerful radios and battery systems so that they don't have to rely on electricity.
And one other reason somebody might get a warning versus someone else could be that there are very specific geographic areas covered by that warning. And so if your cell phone is in that area, you'll get the warning, but not otherwise.
I have another follow-up on communication. I'm not part of the UNCA network, so I don't know kind of what emergency warnings went out to the UNCA system. Y'all talking about being able to notify whoever you called, but was the UNCA system part of that? Did students and faculty receive warnings based on that data that maybe the rest of the Asheville community didn't?
Yeah, I was a student. I am a student, and we got a lot of alerts early in the morning until the big one that was like, if you can, go. And by that time, I wasn't awake. And so when I woke up on the morning of the 27th, I just had a text on my phone saying, I left. People are gone. And I was like, oh, what? And we got like people banging on the doors and stuff being like, you have to sign in if you want food. But it kind of ends like because there was a communication cutoff. It was just everyone being like, you can go to these certain people and ask for stuff, but you don't know, right? And so we did get communication up to the power being out.
Yeah, I'll just say, as a faculty member, I don't know when they called class off. Was it Thursday that they called class, but that was pretty late Wednesday night, maybe Thursday morning. But at the point that students are getting text messages on Friday morning, right, you need to leave, it's almost too late, right? The bulk of the precipitation fell in those 2 days before Helene even made landfall, or I guess not landfall, but made its way through western North Carolina. So there has to be, right, messaging before the storm, the 2 days before, when these forecasts are so spot on, right, to have students make informed decisions about if they need to leave, go be somewhere safe, right? So I think there's a lot of lessons learned, right, in our communication around that whole kind of emergency management piece at the university level.
There was also a pretty severe messaging problem in an email that went out to everybody in the university community. Same message, right? At the top it says, shelter in place, do not travel. And then a little bit lower it said, students, you should go home. This does not make sense.
I would add to that, I'm also a very non-traditional student, but my Thursday classes were canceled Wednesday afternoon. And this, I think at that point, was at it was up to the individual professor to do that before the university completely canceled them. But I feel stupid. I didn't even go out and fill up my gas tank. And I kind of saw this stuff going. We don't watch TV too much, but you know, we look at our weather apps and stuff like that. And we were just firmly in the fat, dumb, and happy. My first warning was Wednesday evening. I live in West Asheville on Vermont Avenue, which has a fairly decent elevation, a lot of drainage by creeks and sinkholes, and there was water running down my street. And I said, well, I'm not going to choir practice tonight. And so this is the kind of decision making, I think, that a lot of people out there make. As you look out there like, oh, heck no, I'm just not going to do that. And then, you know, and then your classes are canceled, and then this, and then that. It's very, you know, and our weather predictions around here are also challenging enough. You know, we look at 3 different weather apps, they all disagree, and none of them turn out right. And again, because of, you know, our geographical locations. So it is kind of hard to get people to get it, I think.
Yeah, following up to that, right, our collective memory of these events is also very short, right? We had similar flooding in 2004, 1961, I'm not sure how many people were around in 1961, or 1906, not 1960, I don't even know. Must be dyslexic today, switching all my numbers around. But those of us who live through Helene, right, if we see these kinds of storms, we know there's a tropical cyclone headed our way, maybe, right, we'll prepare more, hopefully, since we have this experience. But Asheville is full of people who are not from here, right, and they move in and out very frequently. So that's hard too with messaging risks. If you weren't here during Helene and you weren't driving through River Arts the week after it happened, right, to actually see the destruction, how could you ever know, right, that who to trust, right, from the messaging perspective, and how much to take it seriously, especially on social media, right? All these clickbait articles, and, you know, who to trust is a big issue.
I just want to thank everybody who's spoken. I think it's a really great perspective, looking at the wind, looking at the water, looking at the radar. One question I had, and I appreciate you bringing in the perspective of a lot of mobile community. I do think that played a part. And people's perspective from outside. I know one person I spoke to before was from Florida, and they were like, we get water like this all the time. I said, but you're thinking of like an Olympic swimming pool, and we've got land like this. And so again, even those perspectives kind of hurt people because they don't have that lived experience. But one thing I really love the rain gauges and the river predictions. But speaking to some of what's been said in the audience, it was still just a really narrow amount of time. You kind of illustrated, it was just hours before that massive, there were great worded predictions, but it was all just within hours between when it was predicted and people were getting that messaging. I personally heard about this Wednesday morning. You know, I'm trying to implore my spouse to be like, we should get prepared for this. And he's like, you know. So I think it's a great illustration. I think you all did a great job, but I guess my comment or my question is there the opportunity, do we perceive that these models will give us greater foresight. Because if I look at the number of hours between specifically these river models, we're just not even 24 hours in advance in some cases where we really were predicting these massive floods.
Yeah. Like all forecasts, they're improving with time. So 20 years ago, you could get a really reasonable 2-day, 3-day, 4-day forecast just for, highs and lows, rain or not. And over time, now we're pretty accurate out to 7 to 10 days. So I think over time, these river forecasts will improve as we ingest more models and we have computers that are higher processing power and they can get more data, and we'll have even better weather prediction models and hopefully better radar to input into the models, because the models are only as good as the data that goes into them. So I'm hoping they'll continue to improve over time. I mean, 20 years ago, the river prediction models weren't nearly this good either. So. Yeah, I'm thinking. Do you think, the question is, do you think the models will get more accurate as the climate is changing?
Do you think weather will get harder to predict as the models get better at predicting? Like, will it be kind of an arms race with predictability, or?
No, we're actually really good at short-term predictions. The short-term predictions are excellent. It's harder to predict long-term climate. It's a lot more complex than the short-term, but the short-term forecasts are going to continue to get better. So, good questions.
My question is about the National Water Model, and I'm just curious if any of that data goes into Feynman. As a meteorologist in Raleigh for a television station, we're talking about hurricanes usually on the coast, and we use Feynman for flood inundation messaging. So does that data go into Feynman? Do you know?
Feynman?
Do you know what Feynman?
What is Feynman? Sorry.
I know somewhat about Feynman, but it's the North Carolina Emergency Management Systems flood management tool. I can't remember what the exact acronym stands for. I'm pretty sure that data goes into Feynman. I was just at a floodplain conference 2 weeks ago, and they talked a lot about that. So I'm pretty sure a lot of that NOAA, National Weather Service data is feeding into the Feynman tool. Yes.
I'll ask a question if nobody has one. So it's nice that Jared is in the room because he did this analysis. So Helene, right, was classified as a 1 in 1,000 year precipitation event for a large portion of Western North Carolina. So to our panel, what does this mean? What is a 1 in 1,000 year event, and what does it actually represent? And does that actually mean that we won't see another Helene magnitude precipitation event for another 1,000 years, right? We get off scot-free unless we live for 1,000 years.
Can I take this? All right. So, yeah, this is important. A 1 in 1,000 year event means that the probability of that event occurring in any 1 year is 0.1%. So there's a distribution that you can use. It's called the geometric distribution, also called the weighting distribution, where you can plug in this probability of occurrence, 0.1%, and see how long you might wait until that event first occurs. And or at least the probability of waiting that long. And Dr. Crossett, I wrote down some numbers. With a 1,000-year event, the probability, or you'd have to wait 52 years for a 5% probability for that event to happen, okay, for the first time. But in each year, it's still 0.1%. So if it's a 1,000-year event, the probability of it happening now is 0.1%. And if it happens now, okay, the probability of it happening next year is 0.1%. Okay, this assumes a stationary climate. We'd have to wait 106 years for there to be a 10% probability of it happening at some point. Well, really, cumulatively within that, or once cumulatively in that 106 years. Okay, so anyway, that's what that means. It does not mean that we need to wait 1,000 years for it to happen again. It doesn't mean that it hasn't happened in 1,000 years. And the way we come up with these is by looking at the climatology of rainfall events, and we fit a distribution called an extreme value distribution, and there are a few choices for that. But that allows us to extrapolate beyond what has actually happened to look at probabilities of something extreme happening. And so that's where we get these values of precipitation that correspond with 100, 500, 1,000-year events. How's that? Did that sufficiently answer that question? That's a question we get a lot.
Yeah, I think Highland is a really good example of the forecast was spot on, but the communication was wherein lied the error. Just from, not to beat the dead horse of communication, but speaking from a student perspective who lived on campus and wrote out Highland, just the communication on campus, depending on which dorm you lived in, was inconsistent. I lived in Ponder last year, and they gave us this Friday the 26th, or the 27th. They gave us 2 meals throughout the day, and they checked on us periodically throughout the day, like every 4 or 5 hours. Whereas my former roommate who lived in Governors did not share the same benefits and was not checked on throughout the entire day. And the morning of the 28th, they said, go to Highsmith, bring your 1 card, there's going to be a breakfast. And then after that, there's going to be an announcement about what we're going to do. And they said, if you're staying on campus, they had called classes by then. If you're staying on campus, we need your 1 card, your full name, and your written intent that you're staying. If not, leave. And this is after Highland had moved through in Asheville, which was ground zero. So.
This is a comment and a question based on what you were just saying, Dr. Godfrey. So it's interesting when I think about that, and I've told this story to a few people, but take the town of Canton, for example. In just 20 years, they've had 4 100-year plus flood events. Will there ever be a point in the future where we might see those numbers change based on climate variability, climate change? Would we maybe see that 100-year flood, maybe it becomes a 50-year flood or something like that?
Yes, in a couple of months. So we get these data from the NOAA Atlas, and I believe NOAA is updating this. Jared might know more about the timing of that. But yeah, the numbers are being updated. NOAA is working on that. I think they've got a preliminary draft. So those numbers can and do change, and they are changing.
And I'll follow up. Highland and just about every warm season system that we have occur is ultimately can be linked to water vapor coming out of the Gulf of Mexico or the Atlantic Ocean. And we're seeing anomalies, very warm temperatures that we haven't seen before. And as long as that trend continues, the rate of evaporation is going to increase. That means more water vapor. That means more possibility of very heavy rainfall events. So absolutely, as long as the ocean SSTs, the ocean temperatures keep increasing, things will absolutely change.
All right, well, thank you all for joining us for this session. We hope it was informative, and we hope you have a great rest of the symposium.